On number 32, there's several methods to attack this. Here's how I like to think of this problem. Scott can paint a house in 3 hours. That means in 1 hour, Scott paints 1/3 of a house. Caleb can paint it in 5 hours. That means in 1 hour, Caleb can paint 1/5 of a house. Working together, this is how much they can do in 1 hour. 1/3 plus 1/5. If you get common denominators and put those together, that means they can paint 8/15 of a house in 1 hour. So how am I going to do this? Well, 8/15 is basically the rate. The rate times the number of hours, which I'll call H, rate times time, will give me the entire job, 1, and that 1 in this represents houses. So actually, I'd probably put HR for hours. So their hourly rate, 8/15, times how many hours it's going to take them to finish 1 job, 1 house. So the variable is hours. So if I multiply by the reciprocal, hours equals 15/8, or 1 7/8 hours. On number 33, we get into some inequality problems. Remember, the big thing with an inequality is if I multiply or divide by a negative, I flip the inequality. So on this first one, if I add 2x over, and I add 8 over, I'll end up with 5x and 11. At no point did I multiply or divide by a negative. If I divide by 5, I still did not multiply or divide by a negative. So I get, now if I read this correctly, this is saying x is less than or equal to 11/5. So that means things that are smaller than or equal to 11/5, if you think of it in kind of terms of a number line. In interval notation, this would mean negative infinity to 11/5, bracket on 11/5. For number 34, we have a compound inequality. I'm basically solving both inequalities at the same time. I'm going to subtract 4 out to both ends. So now I have -7 less than or equal to 7/3 x less than or equal to 2. To get rid of the 7/3, I'm going to multiply by 3/7. And I'm going to do that on both sides. So on the left side here, 3/7 times -7 would just give me -3. I did not multiply or divide by a negative, so I'm not flipping any inequalities. On the right side, 2 times 3/7 is going to give me 6/7. And all I'm left with in the middle is the x. And so in interval notation, this is everything from -3 to 6/7. I'm including both, so I put brackets on both of them. On number 35, I get into absolute value inequalities. The first thing to do is to get the absolute value by itself. So if I add 5, the absolute value of 3x minus 7 is greater than 17. Now, with the absolute value inequalities, depending on which way the inequality is facing tells me what to do. With the greater than sign, I'm going to separate this into two separate inequality problems. 3x minus 7 is less than negative 17, or 3x minus 7 is greater than 17. Now, before we finish this up, just kind of an aside to kind of show you the logic behind this. Let's say it was just absolute value of x is greater than 17. Well, that means that x could be something smaller than negative 17. Like if x was negative 18, this would work. Or if x was negative 19 or negative 20. So anything smaller than negative 17 technically would work, because when I took the absolute value, it would become big. The other side makes more sense. Anything bigger than 17, when I take the absolute value, it would still be bigger than 17. But I have to solve both of these. So looking at the red side, if I add 7 over, I've got negative 10. Divide by 3, x is less than negative 10 thirds. With the blue stuff, add 7, I've got 24. Divide by 3, x is greater than 8. So I have that x can be smaller than negative 10 thirds. So that would be from negative infinity to negative 10 thirds. Or, which would be that union symbol, x is bigger than 8. That's going to be 8 to infinity. For number 36, this is going to be the other type of absolute value inequality. But just like the first one, or the previous problem, I have to add 5. I've got to get the absolute value by itself. Now, since this is a less than or equal to, now I want anything that's between negative 19 and positive 19. So the stuff that's inside the absolute value goes in the middle, and it creates a compound inequality. So I've got to subtract 10 onto both ends. This will give me negative 29. 4x is left in the middle. 9 on the right. Divide everybody by 4. This will result in negative 29 fourths is less than or equal to x is less than or equal to 9 fourths. Or in interval notation, this is saying give me everything between negative 29 fourths and 9 fourths. I am including those numbers, so I use brackets again. On number 37, this is more of a theory-based kind of problem. The first one, though, we can actually basically attack like a normal problem. Absolute value equals 0. Technically, we always set absolute value stuff equal to positive and negative. But since it's 0, it would just be 0, which means that x would equal 9. So that goes with choice C. Letter B, this is saying that the absolute value of something is equal to a negative. Well, absolute value is distance from 0. It cannot be negative. So this is automatically a no solution. So I don't have to try to solve anything. On letter C, kind of a similar idea here. The absolute value of something, it doesn't matter what it is, it's saying is smaller than 0. Well, being smaller than 0 is being negative. We still cannot do that. Again, this is no solution. Now for letter D, this is kind of the reverse. This is saying the absolute value of something is bigger than or equal to a negative number. Well, all absolute values are bigger than negative numbers. So it wouldn't matter what I plugged in for X, this would always be true. So this one would be all reals. The next grouping of problems deals with inequalities in quadratics and rational expressions. What we want to do here is solve these as if they were equations, but then we're going to test critical points and critical regions. First thing I'm going to do is add the 70 over. This will factor. And it factors into x minus 7, x minus 10. Now, the zeros of this, if it were an equation, the zeros would be 7 and 10. Since it's an inequality, however, these become critical points where I may go from answers that work to answers that don't. So what I'm going to do here is I'm first going to test a number to the left of 7. Easiest one to pick would be 6. Now, the easiest place to test it is in the factored form. So if I test 6 in here, now I don't even really care what numbers I get. I care about positive or negative. If I threw 6 into the first factor, I'd have a negative number. If I threw 6 into the second factor, 6 minus 10, that's going to be a negative number. A negative times a negative is positive. The question is, does this work? Are positive numbers less than 0? No, they're not. So that means anything over there doesn't work. And I always like doing a sad face to show that. Okay, now I'm going to test a number in the middle, somewhere in between 7 and 10. I'll test 8. So now I'm plugging 8 in for X. And again, all I really care about is positive versus negative. If I plug 8 into the first factor, it would be positive. 8 minus 7 is positive. 8 minus 10 is negative. A positive number times a negative would give me a negative. Are negatives less than 0? Yes, they are. So this did arrive at what I wanted. And now I'll test a number to the right of 10. We'll just go with 11. And again, I'm just looking for the positive versus negative here. So if I plug 11 into the first factor, I'd end up with a positive result. Positive in the second one. A positive times a positive is positive. But I wanted stuff less than 0, so that does not work. So the only things that work are the numbers between 7 and 10. Since there was no equal to bar, it's going to be parentheses. My solution set is everything from 7 to 10. Again, don't confuse that with the 0.7 comma 10. That's everything between the numbers 7 and 10. On number 39, it's going to be similar logic. I'm going to factor this first. So I'm going to move everything over. It would be plus x minus 1. This does factor into 5x minus 1, 4x plus 1. So the zeros would be negative 1/4 and positive 1/5. Again, I separate into regions. I first will test a number to the left. Let's say I test -1. And again, all I care about is whether it's going to be positive or negative. So if I plugged in -1, that would make the first factor negative. That would make the second factor negative. Negative times a negative is positive. Again, the question is that what I wanted? Are positive bigger than or equal to 0? Yes, they are. So the left side was what I wanted. If I test a number in between, like let's say 0, that's going to leave me with a negative times a positive, which will be negative. And the question is, are negatives greater than or equal to 0? No, they are not. This didn't work. And if I test something on the right side, say the number 1, that's going to give me a positive and another positive, which will be positive. Those are greater than or equal to 0. So numbers on the right side work. So on this one, it's the outsides that work. So the middle didn't work, but the outsides did. And since we had the could be equal to, we're going to include brackets on those. And so in interval notation, this would be -infinity, -1/4, in union with 1/5 to infinity. And again, I bracketed the numbers because I was including those. Number 40 looks at a rational expression. Now this one has already been factored and I've already got 0 on one side, so we're good there. I'm going to look at what makes both the numerator and denominator 0. The number that makes the numerator 0 would be 4. The number that makes the denominator 0 would be -5. Those are going to become my critical points. Just like I've been doing, I'm going to test numbers in each region. So let's say I test -6. If I plugged in -6 for x, if I plugged in -6 on top, I'd have a negative on top. If I plugged in -6 on the bottom, I'd have a negative on bottom. Negative divided by negative is positive. Does that satisfy what I want? Positive numbers bigger than or equal to 0? Yes, it does. Test a number in the middle. 0 would be a good test. If I plugged in 0, if I plugged in 0 for x, 0 minus 4, that's going to be negative. 0 plus 5, positive. A negative divided by a positive is negative. That is not what I wanted. And lastly, if I test a number on the right, maybe 5. Five minus 4 is positive. 5 plus 5 is positive. That's going to be a positive, which is greater than or equal to 0. So that is what I wanted. So again, just like the previous problem, the stuff that works is the stuff on the ends. Now there is one extra hitch on this problem that I got to be aware of. Yes, the problem says could be equal to, but I know that -5 would cause the denominator to be 0. So I cannot include that. So I'm going to put a parenthesis on that one. 4 makes the numerator 0. That's perfectly allowed. So I'm going to put a bracket on that one. So my final answer is -infinity, -5 with a parenthesis on -5. a bracket on 4 to infinity. Now for the last one on this, number 41, it's going to be similar to number 40, except we're going to have some work to do in the beginning. This is not set to 0. I have to first get it set to 0. So what does that entail? I'm going to subtract over the -2. Well, actually add 2, I guess. I'm going to add 2 so that this is set to 0 now. Now, though, I need to combine these fractions. Think of 2 as 2 over 1. Actually, let me give myself a little space here. I've got to be able to combine these fractions, meaning I'm going to have to multiply this fraction by x plus 6, that's a 6, on top and bottom. So this will turn into 5 minus 2x plus, if I distribute the 2, 2x plus 12, all over the common denominator of x plus 6. This becomes 17 over x plus 6 is less than 0. Now, you can tackle this since it's a little bit simpler than the previous one in a few different ways, but I'm still going to look at it just like I was doing those previous problems, just to be consistent. The only thing that makes anything equal 0 would be a -6. So actually, this only has one critical point, -6. So I'm just going to test numbers to the left of -6 and to the right. So to the left of -6, let's say I test -7. Now I am going to plug it into this inequality because that one has a 0 on one side. So this would be 17, which is always going to be positive. Oop, looked like we had a little error there. Well, we'll bring it back up. No worries. Just a second. There we go. Okay, we're back. So that's going to be positive because it's just the number 17 on top. If I plugged in -7 for x, that would give me a negative on bottom. Positive over a negative is negative. Negatives are less than 0, which is what I wanted. So the left side worked. If I test a number on the right, like, I don't know, let's just say 0, that'd be easy enough. If I plugged in 0, well, the numerator is always positive. If I plugged in 0 for the denominator for x, that would be a positive. That gives me a positive, which are positives less than 0. No, they are not. So only things left of -6 worked. So my solution set would be -infinity. Oops. -infinity to -6. All right, that's where we'll stop this video.